So as Ian said, I work at Yale University. I'm a systems programmer in the University IT department at Yale. So this is a case study, so sort of just to present a story of how we use Moab in one of our clusters. All right, so a little background about Yale. It was founded in 1701, so it's pretty old. It's located in New Haven, Connecticut. It's about halfway between Boston and New York, if any of you don't know. In terms of its size, 5,000 undergraduates, 6,500 graduate students, 4,000 faculty, 9,000 staff. Last year, fiscal year, the operating budget was $2.8 billion, and it has an endowment worth about $19 billion. So it's a pretty well-funded educational institution. A little bit about the actual part of the university I work for. So the HPC group is part of the central IT department, or the IT services of the university. That includes the med school. So we also encompass a number of professional schools. So if you drill down into the organization, the IT organization, so we're under what's called the Research Technologies umbrella. So in addition to managing HPC, they're also involved with responsibilities include managing a research storage system, a campus-wide research storage system, a science network, and other things like the electronic lab. So the HPC group formed as a separate entity in about 2008. It's currently about 9 full-time staff. 5 of them are under the IT department, and the rest are related to other research projects. So we manage 7 HPC clusters, and there is some portion of all these clusters available to all the research facility at the university. So there's effectively an open access policy. All right. So I'm going to talk about one of those clusters we manage. So just to give you the background, to sort of set the scene for this story. So this is what we call a Babel style cluster. So there isn't really much for exotic hardware. Its primary purpose is for biomedical research. So in the local lingo, we call this a life sciences cluster. So we have a pretty good idea of what the workload is for this cluster. So in terms of the type of jobs people run on the cluster, it's mainly sort of single node and variously parallel type of jobs. There's a high number of interactive jobs, and run times typically of days or weeks. So we don't see like a lot of MPI or large parallel type of work being done in this cluster. There's other clusters that people use that kind of stuff. So the background for this is the cluster first formed in 2007, and it's basically been expanding ever since. And so the takeaway from that is basically not all the cluster nodes are equal. So the last round of purchase, which was last year, is a much different beast in terms of the hardware capabilities than the hardware that was purchased in 2007. So in terms of the people involved in this cluster, there's basically 4 groups. So you guys should step up from behind the podium here. So basically at the top here we have the investors. So these are the ones that sort of provide the money to keep this going. So they're the ones that purchase the hardware, and essentially what they desire is really unfettered access to a portion of the cluster they own. So they don't want any kind of restrictions or limitations to do whatever it is they choose to do. In addition, we have the community users. So as I said, a portion of the cluster is sort of open access to research projects at Yale, and in this case it's the biomedical community. And so essentially what they want is some kind of fair access policy to these community resources. Going farther down, the research staff and the developers, essentially they are the ones that work with the first 2 groups. So they're the ones that basically work in terms of the purchasing, brokering, who's going to buy what, and how much, and sort of pulling all the money together. They also work out the service agreements, the SLAs, things like that. They typically provide the tools, especially developers, to see that the actual research can get done. And they also provide value in terms of cost savings, of course, with the purchasing and operational costs and things like that. And then the 4th group, which is what I'm a member of, is basically the IT staff. So we interface mainly with the 3rd group, and they're the ones that basically take these policies and convert them into sort of technical requirements. We provide feedback on the policies whenever we see some issues, and we maintain the operational environment, the working environment, and resolve technical issues when they come up. All right, so here's what was going on. So I guess about a year and a half ago, we got to a point where we were using a workload manager and a scheduler software. It was an open source scheduler software, so it was the Maui software that Ian mentioned, and it just really wasn't meeting our needs. So effectively, the general consensus was the scheduler was the bottleneck, and it was stopping people from doing their work. So there was a lot of unhappiness around there, and these are some of the reasons why they weren't happy. So one of the main things was we had sort of a fixed node policy. So when a person submitted a job to a particular queue, it would go to a particular node. And that really was a problem meeting our SLAs, in the sense is that you had an investor that said, well, you know, I bought whatever, 10, 100 processors, and they don't really care which particular machine it is. They just want their X amount of resources. So when you say, well, I'm sorry, you only get 80 processors today because we had a network outage or something, they're not particularly happy. So we would typically have to do these sort of ad hoc fixes to work around those, and that was a real headache. That was a lot of manual work. So, and the other problem too was the existing policy didn't really account for the different hardware generations. So when someone submitted a job, they could end up on a 4-core node or a 64-core node, which has a huge difference in performance profile. So the users really wanted a way to be able to manage that in control. The other problem is there was no time limit for jobs. So essentially a job ran a node for as long as it wanted, I guess, until the user felt, you know, they were done and they could exit or hang up or whatever. So there really was a low turnover node. So in a sense, you know, when a node is considered idle, it didn't happen very often because people tended to either, their jobs tended to hang out on the node for whatever reason. And also there was community growth. So more and more of the university was using the cluster, and they were competing for a fixed size of resources, so there's longer wait times. They were waiting longer to get to those resources. So those are the sort of the main problems. So, you know, the first thing you do is say, okay, well, you know, you kind of do the whiteboarding exercise where you sit down and say, okay, well, what do we want? You know, what's on the wish list? So these are the 3 main points we came up with. So they really wanted sort of more flexibility in determining, you know, what type of hardware their work would run on. So some people wanted, you know, the many core nodes, some people didn't. So that was sort of the main thing. The other thing too, which was more a requirement from the IT staff, was they wanted to get away from this thing where they had fixed the policies to specific nodes. So there was more flexibility in terms of floating the resources. So when you had an outage, the workload manager would figure it out for you. Would figure it out so you still meet your SLAs, you don't have to go in and manually tune things. The third thing was community access to the idle resources via preemption. So you guys know what preemption is? Anybody? So the general idea there is you have one of these investor-owned nodes, and for whatever reason the investor may not be using it that day, so it's sitting there idle. Well, that impacts your utilization. So the idea is to take one of these community workloads and run it on that idle node. And then when the investor comes along and says, well, you know, I want my stuff back that I paid for, you basically evict the community user. So you just sort of boot them off. So that's called preemption. Questions about that or anything? All right. So we had to find a solution, right? So like I said, the open source product, software using just didn't really meet these needs. So we went to Moab. So the question you can ask is why choose Moab? And the answer is really it was a path of least resistance for us. And I don't mean that in a bad way. I mean that they've done a really good job in positioning their product so they make it easy to transition from an open source type of environment to Moab. And really the main thing why we did that is, that's not going to work, is it really wasn't any change to our users. You didn't have to teach them anything. They didn't have to change anything. It was almost zero disruption for them, right? That's a big plus, right? So that really kept our users happy. So that was one of the main reasons we went to Moab. The other one is we were already using Moab on some of our other clusters. So we already had some experience with it. Didn't have to go and train staff on how to use it. So it was easy to implement in that sense. And the third one, which is what you're paying for, is the support. So, we had to set up a demonstration and convince people it was worth spending money on a workload manager. And Moab really helped us with that in terms of getting this proof of concept set up so we could do a demonstration and say, yes, preemption works, it's not just a myth. And then we could actually do this balancing of the owned resources with some sort of community policy. So, and they also helped us developing the configuration. They gave us a lot of ideas which we wouldn't have thought of on our own, and of course they provided support when we encountered issues. All right, so moving on, how do we accomplish this? So, I guess the two main technology things that we implemented was the preemption, and the other main one is something that's called per partition scheduling. So the idea here is you basically define, you separate your cluster into these abstract things called partitions, and each partition would have your different generation of hardware on it. And then you can customize your limits within that partition to whatever you want. So I give some examples of what it actually looks like inside the configuration files. If you guys are familiar with Maui or something, this is probably something you've seen before. But the idea here is, so we have a couple different sorry, you guys can see this over here? So we have a couple different generations of hardware. So in this case, these are actually Dell model numbers for 2 generations. And so you basically break it out into a separate file, and then within that file you can customize your limits, your policy settings for those. So you can set different group limits, user limits. In this case, we set queue limits within each. So this was a big win in the sense is that I removed the old way we were doing it. We were mapping a specific compute node to a queue and had it more generalized into this sort of grouping or this partition. So that was a big gain for us. It made it a lot easier to manage these resources, and it made it very simple moving forward to add more hardware and manage it and provide the policies. So really the idea here is instead of one of your IT staff going in there and managing each node by hand, you basically let the scheduler figure it out. And it does a good job of this. All right, so the other big thing was the preemption. So basically what we did is we set up a preemption queue across all these partitions. So the idea is we have a separate queue we call scavenge, and you submit your job, your workload to the scavenge queue, and it will find an idle node somewhere and start running on it. And it can be on any of these partitions. It could be on the old hardware, the new hardware, whatever. So the idea is you run there until whoever owns that node comes along and kicks you off. So, and the other thing we got out of this is users then notified when their job gets kicked off. That's something we couldn't accomplish with our previous open source solution. So the only caveat I'm going to say here is the way we set this up, this is a direct quote we got from the engineer at Adaptive, is the way we're doing this preemption, there's a risk of job starvation. So what I mean by job starvation is if you have in your queue, you have lots of little jobs and then one big job. You'll find that the little jobs will tend to fill in the gaps, and so they don't leave enough space for the big job to come in. So we don't have that problem because we know what the workload is for our cluster, and we have basically a lot of these sort of single node embarrassingly parallel problems. There's no one running these large parallel workloads. But if you're in an environment where you do see those, this could be a problem for you. So there's some ways to get around that, but this is what we did because we knew it worked. So, and we've seen it before, so path of least resistance, we went forward with that. All right, so the other parts of this is user education. We had to teach them what a partition was. And really it was pretty simple. So in our environment, they're used to using QSub. If you guys have seen that before to submit jobs. And all they had to do was add this extra flag on there with the partition, and they figure out what type of hardware they want to run on. So it was really simple. And we also set time limits. So that was the thing we were missing before. So we set a time limit for what's the maximum amount of time a job can run. And that really helps for the turnover so resources become idle. All right, any questions about the... Yes, question? So the people that pay for the hardware, we basically say, you don't have to wait, not even 2 minutes. Like I think literally we say you don't wait at all. So even 6 hours for some of these people is waiting too long. And our workloads is such that nobody's running 6-hour jobs, running like a week, 2 weeks. So we could have done that, and then nobody would have used those resources. So, all right. So here's sort of the punchline. So the question is, was this successful? And I can tell you. So here's a graph over here, and this is basically 2012 when we did this. If you can see this little white line, that's eventually when we switched over to Moab. So this is January 2012, December, and this red line is essentially our preemption queue. So we roughly got about 50% more utilization doing this for free. No, we didn't add any hardware. And the other thing too was for the community queues, which is the blue stuff here, the wait time is basically halved because all of a sudden they had access through the preemption queue to a lot more stuff. So effectively there was a group of people that were using the community queue just went and did the preemption, and that worked out great for them. So I put a little star on this. We'll talk about that later. And the other good thing is, so the orange part here is all the owned resources, all our investors, is there was absolutely no change for them. It just went on as before. They didn't have to wait any longer. There was no issues with getting access to the resources, so they were pretty happy with that. So I guess that's not world-shaking in terms of results. So, and that actually isn't really the reason why I think this was successful. I think the reason why this was successful is, we did this 18 months ago, like a while ago, and it's still chugging along. Like, we've made very few changes to this configuration. We've added more hardware, we've had more investors come online, a few have left, our user community is growing, and this is really a stable configuration. So that's why, as a person that sort of runs this on a day-to-day level, I'm very happy with this. I think this was a good way to go. So, compare that to whatever you guys do for Workload Manager and say over the last 18 months, how many times have I had to go in and poke prod things and do things? We've done very little. And also we've had relatively few technical issues. So over the last 18 months, I did a quick count. We opened up 5 tickets with adaptive for problems. And we had very few complaints from the users for this, and a lot of them were mostly relating to vendor tickets. So yeah, that's why I think this was successful. Any questions about that? Yeah. It's gone. It's tossed out the window. I do not. I think actually not that many. I never looked at that. Yeah. All right, moving on. So, it wasn't perfect. Very few things in life are perfect. So, just to give you some ideas there are a few outstanding issues, and the main one we found is if you work from the command line and you use a lot of the command line tools with Moab, they're not really partition aware. They don't really know much about partitions. So trying to get any kind of metrics or reports, that break down stuff along partitions is really hard. So that's still an issue we have. Preemption. So we part of our requirements is we had to change the default behavior for a partition. So what happens is when your job gets booted out, most preemption configurations, it just gets stuck to the back of the end of the line. So it goes back to the end of the queue and it can run again. But what they wanted is they just want the job canceled. It's gone. So that actually turned out to be a little more challenging to do. So that was, we had to actually go into Torque, our resource manager, to make some changes to get that to work. So it's not hard once you know it, but you got to figure out how to do it. So the other issue we've had, and this really hasn't been an issue, is partitions are hard boundaries. So if you do have these large parallel workloads, you can't run them across partitions. The scheduler just won't let you do that. So that's something you want to keep in mind. And also, you can't have a node in more than one partition if you're trying to do some kind of load balancing or something. All right. Questions about that? Anything? So, we did this a year and a half ago. Time marches on. There's been upgrades and bug fixes, but at that time, to get this to work, we had to go into Torque and change the Torque configuration to do it. That was the real sticker for us. So to do the per partition scheduling, we had to go to Moab 7. So that was our first experience with Moab 7. And then we were using an old version of Torque, like 2.4 or something, So we've upgraded Torque a couple times, and this still works. So that makes me really happy, because that doesn't always happen when you upgrade Torque. So whatever we're doing seems to work, and it seems to continue to work. So you know, I get to sleep at night. I don't get phone calls or. All right, so lessons learned, and I guess this is more just sort of general Confucianisms as to actual anything with real need to it. So requirements are not the same as expectations. So when you're dealing with these people that are buying hardware, they may not understand what a workload manager is. Sharing might not be something they're used to doing. So it's better to ask them what their expectations are than try to get actual technical requirements. Also when you work with some other people that do have some technical backgrounds, developers, and you start talking about scheduling, they tend to give you pseudocode or mathematical algorithms. And again, that's really hard to translate into an effective policy because they tend to ignore the fact is they're working in a shared environment. They tend to think of it as sort of isolated. So that is something that we struggled with a lot. So impact. So again, because you're working in this interdependent environment, even small changes can have sort of a trickle-down effect. So that's something you want to keep in mind. So the proof of concept was a big win for us. So that is definitely worth investing the time in if you can do it. And maintenance. So like I said, we've had this running for a year and a half. We've gone through several maintenance windows, upgrades, et cetera, expansions, and just verify the basic, the basic behavior of your workload manager. So verify the preemption works, et cetera, et cetera. So this is all, some of this I guess is common sense. So just to conclude here, I want to say that part of the reason why some of those graphs and some of our results may not look as momentous as you might think. So what we discovered is even this sort of modest increase in utilization of our cluster. We basically took the idea. There was a consensus in the community that the scheduler was the bottleneck for the cluster, right? It was preventing people from doing their work. So we didn't really remove the bottleneck. We just kind of shifted it to somewhere else. And so what we discovered now is our storage system is the bottleneck. It just could not handle the increased workload. So that's part of the reason why the results didn't look as spectacular as they could have. So that's kind of what happens in this business, I guess. All right, so that's it. Questions?